In this lesson, we're going to learn how to show where all the electrons in an atom are located using electron configurations and orbital notations. There are some rules for how the electrons get placed in the atom. The first rule is called the Aufbau principle. And the Aufbau principle says the electron goes in the lowest energy orbital possible. The second rule is called the Pauli exclusion principle. And this rule says that if two electrons are in the same orbital, they're going to have opposite spins. So if one is spinning up, for example, the other electron in the orbital has to be spinning down. They're going to spin opposite each other. So when we're talking about making an orbital notation, basically that's going to show all the orbitals where an electron could be. And we're going to show how many electrons end up in each of the orbitals. So if we were going to take a look at the diagram that we have right here, we can see that we have the first energy level, and the first energy level only has an S sublevel like we learned the other day. And the line that is above the 1s is supposed to represent the orbital. Sometimes it's shown as a line, sometimes it's shown as a box. And we need to remember that in any orbital, there can only be 2 electrons. And then a little bit higher up, because it's higher energy, we see 2s. So that would be the second energy level, and it's also an S sublevel, and there's one line. It can hold 2 electrons. Then we see 2px, 2py, and 2pz. It's still the second energy level because the number in front of it is a 2. But remember, with the p sublevel, we learned there are 3 orbitals. And then above that, we would have the third energy level, which would start with 3s. So looking on our note sheet at the bottom, we have some examples. And we're going to start with helium. So the first question is, how many electrons does helium have? When we look up helium, we see that the atomic number is 2, which means it has 2 electrons. The Aufbau principle tells us that they have to fill the lowest energy orbitals first. So the lowest on this diagram is the 1s. So 1s has to get filled before anything else. And the line would be the orbital, and the orbital can hold 2 electrons, so we're going to put both electrons in the 1s. But Pauli's exclusion principle tells us that they're going to spin in opposite directions. So to designate that they're spinning, we're going to show them as arrows. So one of the electrons is going to spin up with an upward arrow, and we can draw a half arrow or a full arrow. And the next one is going to be spinning down with a down arrow. So the arrows represent the electrons. One in the same orbital, one has to spin up, the other will spin down to show Pauli exclusion principle. So that is an orbital notation. We just finished the one for helium, so congratulations. An electron configuration is just a shorthand. It's shorter than the orbital notation because we don't have to draw in all the lines and label each line as to what it is. We're just going to make a quick shorthand code to show where all the electrons are. It's like a road map to each electron in the atom, similar to the road map shown there on the phone. Now, when we're doing an electron configuration, it would look something like this, where we have a big number, we have a letter, and we have an exponent. So the number in front, the big number, represents the energy level. And in this case, the energy level would be energy level 1. The letter represents the sublevel. Remember, the sublevels are labeled S, P, D, or F. So those are the only letters that we would see in these configurations. And then the exponent is going to represent the number of electrons that are in that orbital in that energy level. So in this case, we would read it as 1s1, and it's telling us that there's 1 electron in the s orbital inside the first energy level. Now let's go back to the helium example and see if we can write the electron configuration for it. So looking at our orbital notation, we can see that both electrons are in the first energy level. So for the energy level, we're going to write a 1. And we can see that they're in the S sublevel. So after the 1, we're going to write an S. And in this case, there are 2 electrons. Each arrow represents an electron. So we have 2 as our exponent. So it's telling us there are 2 electrons in the s sublevel in the first energy level. And there's 2 ways that we can check ourselves with this. First of all, when we add up all the exponents that are shown, they should add up to the atomic number. And the only exponent there is a 2, and that matches the atomic number of helium. So in that respect, it looks like we did it right. There's another way you can check it too, and that is to go back to the periodic table. We want to find the element on the periodic table, and its location should match the ending of our electron configuration that we wrote. So first of all, we're going to take a look at the row that helium is in, and it falls in this first row of the periodic table, and the rows represent the energy levels. So if it's in the first row, its electron configuration should end with the first energy level. Then we take a look at what block it's in, and helium is colored in blue, which means it is part of this block right here, which we should remember is the S block. So that tells us that the configuration should also end with an S. And then if we were to count, helium is not in the first column of that group, it's in the second column of the S block, so it should end with an exponent of 2. And because it does, it matches exactly where helium is in the table, and when we counted up the exponents, it added up to helium's atomic number. We know that we wrote our configuration correctly. So let's try another example. We need to look at beryllium on the periodic table, and its atomic number is 4, so we know it's going to have 4 electrons. All 4 of those electrons are not going to fit in the 1s orbital, but 2 of them can fit there. And remember, we always need to start at the bottom. Our off-bow principle says we fill the lowest first. Pauli exclusion principle tells us they're going to spin in opposite directions, so one is going to spin up, the other is going to spin down. There's 2 more electrons that we're going to need to place, and so we have to go to the very next level, which would be 2s, and both of them are going to fit in 2s because every orbital can hold 2. So again, we would have one point up and we'd have the other point down. Now we have 4 electrons placed, so we're done with our orbital notation. To write the electron configuration, we're just going to say that there are 2 electrons in 1s, so we say 1s2, and then there are 2 electrons in 2s, so our configuration will say 2s2. Now we want to add up the exponents. 2 plus 2 would be 4, so that matches the atomic number of beryllium. We also want to check on the periodic table and make sure the ending of our configuration, the 2s2, we want to make sure that that matches beryllium's location. So we want to find beryllium on the table, and we can see that it's in row 2, which corresponds to energy level 2. So the configuration should end with energy level 2. This is also in the S block, so it should end with an S. And beryllium is not the first element in that block, it is the second element, so it should end with a 2 as the exponent. And since our configuration did end in 2s2, we know we did it right. So there's a third rule that we're going to write down, and it's called Hund's rule. And it states that electrons don't pair up in an orbital if there's an empty orbital at the same energy. Let's try an example with nitrogen. Looking on the periodic table, we see that its atomic number is 7. So we need to place 7 electrons in this orbital diagram. Well, we know from the off-bow principle we need to start at the lowest level first. So we're going to start with 1s. And 1s can hold 2 of those 7 electrons. The next level we're going to go to is 2s. That's the next lowest one. It can hold 2 electrons. Notice how we're using the Pauli exclusion principle to draw the arrows one up, one down. We've only put in 4 electrons. There are 3 more that we need to place, and now we're in the 2p orbitals. All 3 of those p lines are at the same energy, so the electrons are going to want to each go into a different orbital rather than pair up at the same energy. It's very important that we have those p electrons separated. They're not sharing orbitals there. And then if we go to the electron configuration, we see that there's 2 electrons in 1s, so we have 1s2, 2 electrons in 2s is 2s2, and then in 2p we have a total of 3 electrons. Check ourselves, add up our exponents. 2 plus 2 is 4, plus 3 gives us 7, which is the atomic number, and we also want to check ourselves by looking on the periodic table. When we find nitrogen on the periodic table, we see that it's in energy level 2, which tells us that our configuration should end with energy level number 2. Now, N is in the P block. This is our P block over here. So that tells us the configuration should end with P. And if we count, the nitrogen is 1, 2, 3 elements over in that P block, so it should end with 2P. And our configuration did, so again, kudos, we know we did it right. Our last example is going to be sodium. Its atomic number is 11, so we know we need to place 11 electrons. Remember, we always have to fill the lowest orbitals first, so 1s is at the lowest energy. It can only hold 2 electrons, so we put 1 up and 1 down. The next lowest orbital is going to be 2s. So again, we put 1 up and 1 down. Well, that adds up to 4 electrons, which means we need to place 7 more. So once we get to 2p, remember Hund's rule says the electrons are going to go into an empty orbital of the same energy if they can. So instead of pairing them up right away, we need to put one of these electrons in each of the p orbitals. Then we go back in and pair them up. Well, if we add those up, we've only put in 10 electrons. We need one more to make 11. That's going to have to go into 3s. So here's our orbital notation where we've shown where all the electrons are. To do the electron configuration, we're going to say 1s2, 2s2, 2p6, because there's 6 in 2p, and then 3s1 at the end. Let's add up our exponents. 2 plus 2 is 4, plus 6 would be 10, plus 1 gives us 11, so it equals the atomic number, and we should also check with the periodic table. So finding sodium on the periodic table, we can see it's in row 3, which corresponds to energy level 3, so the configuration for sodium should end with a 3. It is in the S block, this is our S block, so the configuration should end with an S, and sodium is the very first column in that S block, so it should end with 3s1. And our example did, so we did it correctly. So congratulations, keep practicing. Thanks for joining me, and I'll see you soon. Bye-bye.